All right, welcome to the first video of statics. Before we get started, I just want to point out real quickly that when you go to the worked out solutions, the different colors mean different things. So in blue, that's just going to be your basic solutions, steps to the problems, things like that. Answers are going to be in red, and then helpful tips are going to be in green. All right. So first we're going to start out with just a basic intro to statics. Now, for whatever reason, statics has this stigma that it's really complicated and it's really hard and nobody passes the class. I don't know where this stigma comes from. Statics is just basic math. If you can do addition, subtraction, multiplication, division, and very basic trig, you're going to be okay. That's all statics really is. The purpose of statics is to model things as vectors and then balance all those forces into equilibrium. Statics is pretty much the science of things that don't move, and so if you can get all your forces or vectors to add up to equal 0, then that particular object isn't going to move, it's static. And that's kind of what we're trying to achieve with statics. So the first thing we want to look at in statics is force vectors. So what is a vector? A vector is often modeled as arrows, and they have direction and magnitude. So, for this section, we want to be able to take different vectors acting on a system or a particle and combine them into one resultant force vector. So, for example, if we have this particle right here, and we have different vectors acting on this particle. Just draw some in there for you. Put some directions. We'll say this is 45 degrees. And we'll say this is 30 degrees. So now they all have direction. This is going to be a right angle right there. And we'll draw some axes in there for you. Y and X, awesome. Okay, so they all have direction. Now we'll give them some magnitude, just to make our math easy. I'm gonna use simple numbers. Of course, in homework or other problems that you get, they're not going to be this simple, but it's the same principle. Just because your numbers look nasty does not mean that the problem is actually harder in any way. So we're just going to give this 10 pounds, this one 20 pounds, and this one 30 pounds. All right? Okay, so now this here, what we just drew, is also referred to as a free body diagram, or abbreviated FBD. Free body diagrams are essential to any statics problem, and as you go throughout your engineering courses, they're essential for any problem that you're going to work out, especially In my background, structural engineering, there's a free body diagram for absolutely everything. Structural engineering is extremely visual, and most of the time, if you can visualize in your mind, put it on paper, draw it out, you can solve the problem. So get really good at drawing free body diagrams. All right, so now that we've got that, we want to be able to split each of these up into different components. So I'll label these forces these vectors or forces really quickly so that way we can keep track of them. I'll just start with this one and we'll call it F1, F2, and F3. So we'll start with F1. We need to split that up into X and Y components. So F1 looks like this. So just by inspection, we can look at that and see that that is all in the Y direction and there is no X direction. So we can say F1X equals 0 pounds and F1Y equals negative 20 pounds. And that's negative because it's going down, not up. As our axes indicate, up is positive, so down is going to be negative. All right, so now we can move on to force 2, F2, and that one looks like this. That's 10 pounds. And so we want to be able to get the X, F2, X and Y components as drawn like that. My F2X is a little off, so I'll fix that. As you can see, they make a square, right? So F2X is going to be that one right there. So that's equal to, using trig, right? We know that SOHCAHTOA, right? We all remember that from trig? Okay, so F2X is going to equal a positive, right? Because these arrows all need to be going in the same direction. So it's going to be positive 10 pounds times the cosine of 45 degrees. And that's because of this middle part of SOHCAHTOA. So we know that the cosine of 45 equals adjacent, which is F2X, all over hypotenuse, which is 10 pounds. So you can rearrange this to get this. A lot of times we just skip this step right here because we can go straight to here. But this is how we got to here. If you need at the beginning and you don't see this right away, write this step out every time and then move on to this step. However, it's pretty basic once you do it, 2 or 3 times that you can see that it's going to end up like this, so you can skip this step entirely. All right, so you can just plug that into your calculator and you can get the answer for that. I calculated that. I got 7.07 pounds. It's extremely important that when you're plugging this into your calculator that it's in degree mode, otherwise you're going to end up with a really janky number. And that's probably where you're going wrong if you're not getting that same answer. Also at this point, if you're going through one of these videos and you see a mistake that I make, please let me know. I'm human. I definitely make mistakes. I'm not perfect. I'm gonna make errors. So let me know so I can fix them. And then that way, you know, other people aren't running across the same problems and not realizing it. But yeah, please let me know. All right, so now that we have f2x, we can find f2y in the same way. So for the y value though, we're gonna be looking at this first part of SOHCAHTOA. So the sine of 45 is equal to the opposite, which is f2y in our case, all over the hypotenuse, which is 10 pounds. So we know that 10 pounds times the sine of 45 is going to be equal to f2y. So we know that 45 is going to be the same as cosine of 45. So we can just write that down, or we can double check when we put it in our calculator, and we should end up with that same 7.07 pounds. Okay, again, you don't need to write out this step right here, but if you're having trouble seeing where this comes from, write this step out until you can see it, then you can just go ahead and skip right to that step. All right, so now let's look at F3. So F3, if we scroll up a little bit, F3 is gonna look like that vector right there, where we draw this out. That is gonna be F3x and F3y. Because in order to get these x and y components, you literally just make a triangle out of your vector, right? And so then that's x right here, and then this is y, but we can just move y parallel over to there. You can write it either way, it doesn't matter. Just remember that x and y are gonna originate where the vector originates, which is right there. Okay, so we're gonna find these the exact same way as we found the other ones. So we know that this is 30 degrees, and so we're gonna use SOHCAHTOA to find the x and y components of F3. So F3x is going to equal, let's see, this is 30 pounds. 30 pounds times the cosine of 30 degrees, which if we plug that into our calculator, 30 times cosine of 30, make sure again your calculator is in degree mode. I get, if rounded up, we get about 26 pounds. And so then we can find F3y, which is going to be equal to 30 pounds times the sine of 30, which is going to be equal to 15 pounds. All right, so now that we have it all broken up into components, we can now combine the components. So we couldn't just add the forces straight across before because all the vectors were going in different directions. But now that we split them up into similar directions, we split them all into x into y, we can now add all the x and we can add all the y because those are all now acting in the same direction. All right, so I'm going to combine components. And before I do this, I like to do one last check of all of the forces to make sure that I have things going in the right direction. Because sometimes I can get so caught up in just finding what the force is, like the component value is going to be, that I forget to pay attention to the direction of the force. So if we come up here and we look at force 1, we can see that it's going down in the y direction. Okay, good, negative. And there's nothing in the x direction. All right, that makes sense. And then we can come and look at F2, and we can see, okay, it's going positive in the x, positive in the y, positive, positive. Okay, so we're all right there. And then we come down to F3, and we see that the x is going in the negative direction, and we left off that negative sign, so we can go ahead and add it there. And the y is acting the positive, and we have a positive there. All right, so we're okay now, which again is why I like to go back and double check everything, because it's really easy to just drop a negative sign and then it messes up your entire problem. So it's really good to get in the habit of just double checking yourself as you work through problems so you don't get to the end, have the wrong answer, and then have to go back through and redo everything. If you can kind of double check yourself at every step, then it makes less work for you and it's less time consuming. All right, so now that we're ready to combine our components, let's start with our x components. And you can literally just add them up. So your f resultant in the x direction is going to be equal to f1x plus f2x plus f3x. So f1x was 0 pounds, f2x is 7.07 pounds, and our f3x is negative 26 pounds, for a grand total of negative 18.9 pounds. Now, every teacher or professor is going to be a little bit different on how they want you to round your answers. For me, and especially when you get into the field, you're going to want whole numbers. Again, teachers get kind of finicky about your decimal places, but I'm usually just going to round to like 1 decimal place or to the nearest whole number. So for me, FRX is going to equal negative 19 pounds. Again, your teacher might be a little bit more finicky and want you to stay at 18.9 or 18.91. Again, it should all be the same. You shouldn't get docked points. You might, depending on if they tell you to specify to so many significant figures. But for me, I'm just going to use whole numbers, so 19 pounds. All right, now we can add up our y components. F resultant in the y direction is going to be, again, you literally just add them up. That's why we split them up in the first place, is so that we can add them together. So we're going to do f1y plus f2y plus f3y. So f1y, we had negative 20 pounds. f2y, we had 7.07 pounds, and f3y we had 15 pounds. So if we add those up, we get 2.07 pounds. Again, I'm just gonna round mine. Your teacher might be different, but I'm just gonna say it's 2 pounds. All right, so now we have our resultant x component and our resultant y component. And so now in order to get our just straight up resultant force, we're gonna use Pythagorean theorem. So essentially what we have right now, if we were to free body diagram it, because that's really important to remember how to do, we have our particle that we were looking at, and now we have an x force acting on that particle at negative 19 pounds. So we can draw that like that. And then we have a y component at 2 pounds in the positive y direction. So we've got that right now. So if we draw a box from those components, right? Then we can draw a diagonal through that rectangle and create a hypotenuse to a rectangle. So if we blow this up right here, we get something that looks like that. Where this is going to be 2 pounds right there, this is going to be 19 pounds, and this is going to be our hypotenuse, hype, if you want to abbreviate it. That's how I abbreviate it anyways. And now this hypotenuse right here, that's our resultant force. Right? So just as we did up here, we broke a force down into components. We're now going backwards. We have components and we want to get that force. All right. So in order to do that, we can all remember Pythagorean theorem from, I guess we learned that probably in trig. And we know that when we have a right triangle, which we have here, we have this equation, a squared plus b squared equals c squared, where a is one side of the triangle, b is one side of the triangle, and c is the hypotenuse. So if we solve for c, we get c is equal to the square root of a squared plus b squared. So we can now solve for our resultant force. So we're going to use this, and we're going to get force resultant is equal to the square root of frx squared plus fry squared. So it's going to be equal to the square root of negative 19 pounds squared plus 2 pounds squared. Which, if we plug that into our calculator, we get, all right, 19.1 pounds. Now, you may be asking yourself, well, if we're just going to square these numbers, why does it matter if we know that it's negative or positive? Because when you square a negative number, it's just going to end up positive, right? Well, it's important because of this right here and here. It lets you know which direction that force is acting in. If we didn't keep track of the positive or negative, we wouldn't know if this because this vector is acting this direction, but we might think it's acting this direction, or even this direction, or this direction. So it just gives us that direction. We know that it's got to go negative 19 in the x and then positive in the y. So it has to be that vector instead of all the other ones. Otherwise, you would have the magnitude, but you wouldn't have the direction of that vector. All right, so again, I'm just gonna round my final answer off, and I'm gonna say FR equals 19 pounds. And that's your resultant force. It's as simple as that. Really not a big deal. Another thing that might be asked for is, like I said, the direction of that vector. They might want you to draw it. They, might ask for an angle. There's a couple different ways they might ask for it. But it's all about visualizing it. If you can draw it, you can answer the question. If we draw this triangle of our resultant force again, that one's not as to scale. That's 2 pounds, that's 19 pounds, and now we know that this is also 19 pounds with a little extra decimals on there, but I don't need it to be too exact. All right, so one thing that they might ask for is this angle here, or they might want something like this, where if you have your x and y axes, they might want the angle counterclockwise from the x-axis, which is a common one. They might want it from the y-axis. I haven't really used that one as much. The most common is they'll either ask for this angle here and what quadrant it's in, or they'll ask, this is the most common, they'll ask for the positive x-axis counterclockwise to your vector, so that angle there. So for both of these though, you're going to need this angle right there. So again, going back to SOHCAHTOA, we can really use any of these because we've now found our hypotenuse. It's fine. I like to use this one the best just because you can do it without finding your full-on resultant force or without finding your hypotenuse. You can do this step before you do that step. Depending on how you like to do it. It doesn't matter which order you do it in. Personal preference. You're going to get the same answer either way. So we know that the tangent of theta is equal to the opposite over adjacent. So in this case, that's going to be equal to the opposite is 2 pounds, and the adjacent is 19 pounds. So if we want to solve for theta, it's going to be equal to the tangent inverse of 2 pounds over 19 pounds. Also, while I'm calculating this, it's just probably important to note that I'm keeping track of my units. I know it might seem a little ridiculous at this point, but trust me, in the long run, you're going to want to get into the habit of writing units on everything. Units are so important, and it's really important to make sure that your units are consistent and that they're being canceled out correctly, otherwise, or that your unit versions are even correct. Otherwise, you're going to run into huge problems. All right. So I get theta equal to 6 degrees. So again, this up here is not drawn to scale at all, but that's okay because it's just a visual representation. So now that we know that that's 6 degrees, you can either draw little axes and put theta there, and you can indicate that that's what you mean by theta equals 6 degrees. Or if they specifically ask for, you know, the angle from the positive x-axis counterclockwise to your vector, then it's going to be this 180, right? Because a straight line is 180 degrees minus that theta. So we'll just name that angle alpha for now and say alpha is going to equal 180 degrees minus 6 degrees. This is going to equal 174 degrees. So you can either box this right there, or you're going to end up boxing that right there. And again, if there's any confusion at all, you can always draw a picture next to this one as well and just say alpha and call it good. And that's, you know, pretty basic, but should get you there for just a basic intro to force vectors. Again, if you have any questions about this video, if you can't read my handwriting, which again might be a problem, or if there's any mistakes in here, please let me know. I'll get them fixed. You can send me an email at Taylor's Tutoring, etc. at gmail.com, or you can just use the chat function at the bottom of this web page on our website. Again, question, comments, concerns, feel free to email me, and I'll get back to you as soon as possible. Thanks for tuning into this video.